Assalamualaikum warahmatullahi ta'ala wabarakatuh, and good morning everyone. Firstly, let me introduce myself. My name is Technologist Pirawan Saparuka, the lead author of this study. I'm from Department of Mechanical Engineering at Politeknik Kota Kinabalu, Sabah, Malaysia, with extensive experience in mechanical system design and impact analysis. I have dedicated much of my research to the study of crash resistance and structural integrity of materials. The second author, technologist Muhammad Nasri Hashim, comes from Department of Electrical Engineering at Politeknik Kota Kinabalu, Sabah, Malaysia. His knowledge of sensor technology and control system has been crucial in refining our experimental setup for this study. And Mr. Sarapudin Rapin, our third co-author, is affiliated with Division of Automotive Technology at College Community Tawau, Sabah, Malaysia. With a background in automotive engineering, he has a strong interest in vehicle safety mechanism, particularly in the context of automotive crashworthiness. We are delighted to present our work titled A Comprehensive Study on the Crash Resistance of mild steel thin-wall tube under low speed impact condition. Introduction. In this section, we will introduce the fundamental aspect of our study. Steel, as we know, is an alloy composed of iron and carbon. It is renowned for its mechanical properties such as strength and fracture resistance, which make it a preferred choice in engineering application. Among the many types of steel, mild steel stands out due to its high strength, stiffness, and lightweight properties, making it ideal for structures that require efficient impact response. The core objective of our research is to evaluate the crashworthiness of mild steel thin-wall tube, focusing on their behavior under axial loading condition. Specifically, we investigate various cross-sectional geometries, specimen length, and their corresponding energy absorption characteristic. To elaborate further, this study emphasizes three key focus areas. Number one, we explore the structural influence of circular and square cross-sectional tubes. Number two, the length of each specimen is standardized at 120 mm to maintain consistency across all tests. And number three, understanding how these thin-wall tubes absorb energy during axial compression is critical for improving crash safety design. Physical or experimental tests. Moving on to the experimental setup, we employ a low speed impact testing method at 2.75 mm per minute to simulate crash condition. The tests were conducted using an Instron machine with a 100 kN load capacity fitted with a 200 mm diameter platen impactor that complies with ASTM 3763 standards. The clamping system was designed to provide coaxial alignment within the upper and lower rigid components, ensuring the specimen were properly secure for accurate testing. The support region had a diameter of 120 mm, matching the specimen dimension. Specimens materials. The material used for specimen were sourced locally and comprises of Q235 mild steel. The two types of geometries were tested. First one, columnar tube. This had a square cross-section measuring 40 mm across. And another one, cylindrical tubes. This had a circular cross-section with an outside diameter of 37 mm. Both types of tubes had the same length of 120 mm and were thickness of 1.5 mm. This uniformity ensured that the differences in crash performance were due solely to geometry rather than material or size variation. Key parameters. To assess the crash performance of the thin wall structure, we focus on 5 key parameters. Number 1, maximum crushing load, meaning the peak compressive force before plastic deformation. Number 2, total absorbed energy, means the total energy consumed during deformation. Number 3, average crushing load. This represents the average force experienced during the compression process. Number 4, crushing force efficiency, means a ratio of average to maximum crushing load, indicating energy absorption efficiency. And number 5, specific absorbed energy, means the amount of energy absorbed per unit mass, which is crucial for assessing material performance in lightweight application. Crash sequence columnar tube. The crash sequence for the columnar tube, illustrated by the load displacement curve, shows 4 peak axial loading values at compression displacement of 2 mm, 35 mm, 55 mm, and 80 mm, indicative of progressive buckling behavior. Initially, the specimen exhibits front buckling with inward deformation at the top, followed by splitting and friction generation. This behavior is characteristic of square cross-section under axial loading, and it highlights how geometry influences buckling patterns and energy absorption. Crash sequence cylindrical tube. In contrast, the cylindrical tube exhibits 2 distinct axial loading peaks at displacement of 5 mm, 20 mm, 31 mm, 45 mm, and 60 mm, with the final buckling occurring between 70 mm and 75 mm. The deformation mode remains as progressive buckling, but unlike the columnar tube, the first lobe formed at the lower part of the specimen. This sequence initiates a concertina mode of buckling, where the material folded outward, demonstrating the influence of circular cross-section on deformation pattern. Crashworthy capacity. Our analysis revealed distinct differences between the two specimens. First one, cylindrical tube specimen C120. This specimen had a lower maximum crushing load of 72.40 kN, but a higher average crushing load of 37.54 kN and a superior crushing force efficiency of 51.80%. The specific absorbed energy was also higher at 11,349.46 joule per kilogram. The second one, square tube or columnar tube specimen S120. It achieved a maximum crushing load of 80.4 kN with an average crushing load of 23.44 kN and a crushing force efficiency of 29.15%. The specific absorbed energy was measured at 10,789.66 joule per kilogram. This result indicates that the cylindrical tube performed better in terms of energy absorption despite having a slightly lower maximum load capacity. Final deformation patterns. Finally, the deformation patterns observed were quite distinct. Looking at columnar tube specimen, these form a symmetric fall in a contiguous or compact pattern, often occurring on opposite planes. While looking at cylindrical tube specimen, these develop symmetric fall with a concertina or ring pattern forming at uniform intervals. Understanding these deformation patterns is critical for designing materials and structures with improved crashworthiness. Summary and future work. To conclude, our study highlights the superior energy absorption capacity and crashworthiness of the C120 cylindrical tube thanks to its high crush force efficiency and specific absorbed energy values. For future research, we propose expanding our investigation by testing under different loading conditions and exploring alternative materials and geometries. This will further enhance the crash performance of thin wall structure in a real-world application. Thank you for your attention. We would like to extend our gratitude to the Research and Innovation Polytechnic grant from Jabatan Pendidikan Politeknik dan College Community JPPKK for supporting this work, and to the Department of Mechanical Engineering and Department of Electrical Engineering in Politeknik Kota Kinabalu, and also the Division of Automotive Technology in College Community Tawau Sabah for providing the facilities required to complete this study. We look forward to any question you may have. That's all.